Okay, we're going to continue with our discussions on premixed flame combustion, but now we're going to talk about flammability limits and flame quenching and ignition. So I want to actually direct your attention first to a very useful YouTube video. So take a look at this www.youtube.com, and it's under Fundamentals of Combustion. So it's Lab 6, Premixed Flame Propagation and Flammability Limits. And so I'm assuming that you're able to see that. Yes, you are. You're able to see that. So let's look at the apparatus, and we'll discuss how this is relevant to some of our discussions. So,
okay, so
let me turn.
What we're doing is we have a chamber that's sealed on one end and open on the other. We are pre-mixing the fuel, and we have two hoses, one that has compressed air, one that has fuel, and we bring them into a T, which is brought in right here on the end of the tube on a small jet. On the other end, we've got an igniter on the open end, and throughout the volume, we have 5 thermocouples and 5 photosensors. So we're able to look at the propagation of the flame as it comes from the open end through to the closed end. We're going to be looking at the flame speed and the temperature of the flame. And we're also going to be able to look at, since it's a clear glass tube, the transition from a laminar flame to a turbulent flame. And as soon as it becomes a turbulent flame, you'll see the flame accelerate quite rapidly.
So a couple of things that we've talked about. We talked about this idea of ignition at an open end. And so I asked you last time to understand better what happens when you have ignition at an open end and you're propagating into reactant stream. So as you propagate into this reactant mixture, as we noted before, because the velocity at the closed end is 0, the velocity of the reactants is also 0. The propagation speed then has to be the laminar flame speed, because the laminar flame speed, as we discussed, is the speed at which the front overtakes the reactants. So if the reactants are stationary, the observed velocity of the front is, in fact, the laminar flame speed. Now, there was another point that this person mentioned, and that's the idea of a flammability limit. And so you know from experience that if we have a vessel full of air with just a little bit of fuel, methane again, we try to ignite that, we're not going to get a flame. We're not going to get a propagation process. Similarly, if we have a vessel full of methane with a little bit of oxygen mixed in, we're not going to get ignition there also. So we understand that when we are at extremes in the concentrations of fuel or oxidant, that the reaction process doesn't take place. I'd like you to think about possibly why this might be true. And so let's look at the case, for example, where there's just a little bit of fuel in this huge sea of oxygen. Now, you know from experience and what we've talked about earlier in the class that it takes just a small amount of fuel and oxygen together to get this flammable mixture. Anything else that you carry around acts as a diluent. So I'm going to make a mental note to write that word down. So diluent. So in that dilution process, the bonds that we break as we change the reactants to products have to be used to increase the temperature of the products and the diluents. As an example, nitrogen is a diluent that we carry around when we do combustion in air. The fact that we have the nitrogen reduces the final temperature that we're able to achieve. If we burn a fuel vapor or fuel gas in pure oxygen, we achieve much higher temperatures than if we burn it in air, because the energy associated with the bond breakage of the reactants that is available to heat up the products has to also heat up that nitrogen. So if you think about it, if we have this sea of air on top of whatever was necessary just to consume the fuel, it's an inadequate amount of fuel to cause a temperature increase that will be allowed for self-sustaining reaction. And so we're going to get to discussing this in more detail, but right now let's watch this video. So there's, again, a description of what the experimental configuration is. We will go to 5 minutes, 3 seconds or so and restart it. And what you'll see is from this, they've reduced the lighting so that you can see the luminescence from the flame. When we looked at the diffusion flame, if you recall, we saw that the diffusion flame was bright orange. Why was the diffusion flame bright orange? Because the solid particles, the soot particles in the flame were radiating broadband and allowed us to see this orange glow. Here he has an igniter, and you're seeing that igniter as orange, which is because it's a solid. And when he ignites this mixture, you're going to see this mixture as blue, and that blue is chemiluminescence from the CH stretch. So it's the carbon-hydrogen bonds that are stretching that we're actually going to see, and that's going to be the marker of this premixed flame as it goes into the reactant stream. Now, as we go towards the flammability limits, the flame velocity, the flame speed goes smaller and smaller, and all of a sudden it starts to compete with what you might get from buoyancy-induced velocities in this system. So when you look at high temperatures and you look at the types of temperatures that you have in a combustion system at normal pressure and gravitational conditions, you get buoyant type velocities on the order of 5 to 10 centimeters per second. As you look at flame speeds for the weakest mixtures that you could possibly ignite, all of a sudden now they're starting to be comparable, and so you see a distinct leaning and buoyancy-induced sort of flow artifact to the flame as it propagates across. So I wonder if I could do this full screen and play, okay? So here's the ignition, and there's the process. Let's take a look at that again. So, ignition, and I'm going to pause it after ignition. So you see that front and how it's leaning, and it's leaning because of the buoyant conditions in there, but it is propagating. So this mixture is within the flammable limits. It's propagating at what we would think about as a laminar flame speed because it's a closed end and propagating essentially into a stagnant mixture. At the end, because it had leaned the way it had leaned, all of a sudden you're getting this more significant expansion out the back, and so there's a lot of other stuff that was left in there because it was not a full-strength mixture. Okay, good. So again, you have an idea of what some of these issues are as far as sort of qualitatively what we would expect to see. So let's talk more quantitatively about the issues. So we're going to talk again about premixed flame limits and flame quenching. So flammability limits and quenching. So here we're talking about the flammability limits. The flammability limits are the lower and upper limits between which a mixture is flammable. So when we saw in that YouTube video a case where the flame was able to propagate, if we were below this lower flammability limit, so if our equivalence ratio is below the lower flammability limit and we ignited, we sparked at this open end, we wouldn't get a flame to propagate there. We'd burn up, whatever is local to that ignition source, but there's nothing else that would happen. Now, the way we talked about that initially is that there's this process of dilution. So this notion of a diluent. So as an example, again, my favorite example, methane. So if we have methane, we know for a methane flame to be to burn stoichiometric conditions, and we'll check this. That we need 2 moles of oxygen for every mole of methane. We need, so let's just, again, let's do our carbon balance. Our carbon balance says there's 1 carbon on this side, 1 carbon on that side, 4 hydrogens, 4 hydrogens, 4 H2O, 4 O2, 4 O, 4 O. So from an elemental balance, we're happy with that. And we understand that there's a certain amount of energy that's released here. So there's as we say, there's an enthalpy of combustion associated on a fuel basis that says for every gram of methane that I use, I give off 44 kilojoules per gram of methane consumed. So this looks like about 44 kilojoule per gram of fuel. All that energy has to be able to increase the temperature of the product gases. And this is, again, from our enthalpy versus temperature graph. So that's the stuff that allows us to increase this. Now, having said that, now imagine what would happen if we added quite a bit of air here. So I'm going to say 47.6 moles of air. So 10 times our 3.76 N2 and O2. All that stuff gets carried onto the backside because we've already used the amount of air necessary to get a reaction. So the amount of air required for the reaction is this, 2 times 4.76 moles of air. So all this additional stuff is just a heat sink. And that's the way you want to think about this diluent. This diluent, this stuff that we don't consume, that is only a dilution, can be thought of as a heat sink. And because it's a heat sink, it doesn't allow us to get our final temperatures to where we want them to get. So if our final temperatures aren't getting as hot as we need them, it's those burnt gases that become the ignition source for the next wave of reaction to take place. So from that sort of perspective, in a weird static, so this is like a conduction model of fire. Let me just tighten this. So a conduction model of fire might say that you need a certain amount of conduction from the burnt gases into the unburnt gases to get the reaction to self-sustain and to get this wave to continue to propagate. So you have, say, an initial temperature of your mixture. You cause ignition to happen and get a high enough temperature locally because of ignition, and then you take that ignition source away. If you've taken that ignition source away, then basically, you've caused this to happen, and the equilibrium is going to be some low temperature here. So if there's no reaction, the equilibrium temperature is going to be low because you're just mixing this little bit of hot gas with all this other stuff, and you get a slight bump in the temperature. But maybe I need a temperature close to whatever this ignition temperature was to get reactions to take place. What I need is I need a conversion process that says that once I get this guy, the next element, hot enough, and so that hot enough might be just some secondary adjacent temperature. Once I get that guy to be hot enough, then I really get a boost in the temperature associated with it. Then I get this guy to ignite the subsequent layer, and that, and that, and that. So it's these successive ignition processes that allow a flame to propagate. Having said that, the temperature of whatever the unit of interest has to exceed an ignition temperature in order for it to ignite its neighbor. And again, with more dilution and with more heat sink elements in there that aren't contributing to the reaction, we're unable to achieve that temperature. So, I'm sorry, this is this should not be what I was trying to show here is not, well, I can either show it in terms of the ignition energy, or I can also show it in terms of the okay, this is good. This is the ignition energy, and if I wanted to do it sort of separately, I could do it in terms of the flame speed. So I can do flame speed versus phi L, phi U, where these guys fall off. So there's some value of phi L where the laminar flame speed is no longer defined, and there's some upper limit where it's no longer defined. Again, the L here is for, it's either for lean or lower. The U here is a marker of the upper where it's too rich. So we have a lower flammability limit and we have an upper flammability limit. Okay, to better describe this, we want to review some ideas in terms of descriptions of gas models. So we're going to start talking a little bit about gas models and the relationship between mole fractions, mass fractions, and pressure, partial pressure. So we're going to talk about mass fractions. And mass fractions we've used before, but we typically denote Y sub I. Mole fraction, we typically denote X sub I, and the relationship between the two. So if we have some vessel where we have species B and species W, we can talk about the mass fraction of species I in terms of the mass of I. I'm sorry. And we want to talk first, we'll talk about the density, and then we'll talk about the mass fraction. So the density of any of these is just the mass of I over the volume of I. So this can be, again, B or W. Yi now is the mass fraction, is mass of I over the total mass. It's evident that Yi is just rho I over rho, or that rho I can be written in terms of the overall density times Yi. And again, an obvious sort of construct or result of this is that if we sum rho sub I, so the sum of the individual densities written in terms of the mass fractions, we get a result that says that, you know, the total density, so this is rho, is equal to rho times the sum of Yi, which just tells us that the sum of the mass fractions are equal to 1, which again is sort of an obvious issue. All right, similarly, we can talk about the mole fraction, X sub I, as moles of I over the total number of moles. And we want to relate this to either the partial pressure or also to the volume fraction. And so there are two gas models that we're going to review, and that's Dalton's law and Amagat's law. And so in Dalton's law, we model the total, we model the gas elements as being individual, occupying the same volume, but at different pressures. So we have independent gas molecule systems and simply in an additive sense then where each is occupying the same VT, we can think of the partial pressure of species 1 as just this P1, and P1 over PT is equal to XI. So PT is equal to P1 plus P2 plus P3. And you can show this pretty simply using the ideal gas equation state. So if P total is equal to that, clearly sum of PIs, which each individual one is Ni over V total universal gas constant. So they're all the same temperature, they all occupy the same volume, and so Pi is equal to that. If we divide by P total, just for completeness. So if we divide any one of those by P total, so this is the definition of P total, then we'd have a Pi over P total, again just as Ni over N total. So it's easy enough to show from ideal gas. For Amigat's law, same idea, except that what we're thinking about now is that all the pressures are the same, so same P, same T. So same here for Dalton, same V and T. So here it's same P, same T, and we show that the volume fractions are just the mole fraction. Okay. So when you look at descriptions of, for example, flammability limits, and the flammability limits are given in terms of volume fraction, you understand that you're talking about a mole fraction also. Okay, so now going between mole fractions and mass fractions. So fundamental definition of the density. The density can be written in terms of rho times yi. It's the total density times the mass fraction. The definition of the mole fraction, of course, is, again, Ni over N total. And so when we think about, for example, the mixture molecular weight, so molecular weight is going to be the total mass divided by the total number of moles. So it's going to be the individual moles of I times the mass molecular weight of species I divided by the total number of moles. And so we clearly show that that's simply sigma xi mi. So it's the sum of product of the mole fraction and individual molecular weight. So for air, just as this model, we understand that air. So remember, here's I hope you've seen this before. So when we write air from modeling, I think we talked about this before. When we write air, we have 1O2 plus 3.76 moles of N2. So this is 4.76 moles of air. Okay. Okay. So when we talk about the composition of air, the composition of air is so the mole fraction of oxygen in air is 1 over 4.76. And obviously for nitrogen, it's 3.76 over 4.76. Okay, so when we're looking at the mixture molecular weight of air, this 1 over 4.76 is our 0.21, so it's 0.21 times the molecular weight of O2, which is 32. So it's 0.21 times 32 plus 0.79 times our mixture molecular weight of N2, which is 28. And so we get 28.8 as our mixture molecular weight of air. Now, again, we can relate yi to xi by using the definition of yi, mi over m. We can talk about this in terms of the mole fraction times the molecular weight of I divided by the mixture values. And we've already talked about what the mixture molecular weight is, and so it is this simple relationship. So yi is equal to xi mi divided by sigma xi mi. Okay. We've already used ideal gas in all the problems that we're talking about. I don't think there's any reason to. Oh, there's one reason to talk about this. So the ideal gas law that we've always talked about is for, the way that you perhaps learned it whenever, freshman chemistry or high school, is obviously just for it's single component. And I guess all I want to make sure to remind you is that if it's multi-component for a mixture, that all we have to do is we have to simply correct it. And the correction is that P is equal to the sum of the partial pressures. Remember, PI is what we call a partial pressure. And so there's nothing there. It's, we're Ni over V R star universal times T. So that's okay. And the only twist, if you will, is that what we're going to do is we're going to expand our NIs either in terms of the mole fractions or in terms of the mass fractions. And I think it makes more sense to do it in terms of the mass fractions here. So Ni over NT xi, yi is our xi mi over m mix. We've already talked about that. And so we can simply rewrite this, substituting the definition of yi into this system. We can write this in terms of the total density and again, this is R star T sigma yi over mi, okay? Now, what we've really done in a sort of interesting way is that we're essentially thinking about this maybe more as if we divide R star by a mixture molecular weight, then we're going to get a mixture value of the gas constant. And so this is really, in some sense, the modification to get us to that point. So this is, again, just a property definition for the gas mixture values of ideal gas. All right, so get us back into looking at flammability limits. The U.S. Bureau of Mines really led the development of flammability limit data for mine workers who encountered all sorts of different hazardous environments. And so if you look at methane as an example, the volume fraction of methane in air at the lower flammability limit is 5%. At the upper limit, it's 15%. So we are writing it in terms of mole fractions. We understand those mole fractions are the same as volume fractions. These runs are 25 C and 1 atmosphere, sort of like the standard test. So the way that they do it is that they really just ignite in an open vessel and see if the flame propagates to a certain extent or not. So the lower flammability limit is given as the greatest non-flammable mixture and the least flammable mixture. It's an average of those, whereas the upper is given as the greatest flammable mixture average with the least non-flammable mixture. So it's a very simple test to establish and to come up with. So as we look at our lower and upper flammability limits for a range of fuels, we see that, again, methane, ethane, propane, we're all talking about 5, 3, 2%, where things are a little bit wider in terms of flammability limits. I don't have it here. Hydrogen has a very wide flammability limit. Carbon monoxide has a very wide flammability limit, but these are things that we can find in the literature. But again, we see that on the upper end, we're at from really about 8 to about 15 for methane, and again on the lower end, it's about 1 to about 5 for methane. Now, sometimes we encounter mixtures of gases, mixtures of fuels. And we want to establish what the flammability limit is for the mixture. Well, towards that is really a very simple concept that's true for alkanes, and that is that there is a fuel energy density that allows for the mixture to be flammable. And this is really true more on the lean end. So this is really a lean flammability limit model. The rich is a little bit more complicated, but the idea, and it's a really clever idea, is that, again, that there's an empirical fuel density that's required for ignition. Let's say 50 gram per meter cubed. And then when you multiply that by your typical alkane heated combustion, you find out that really it's about just, this is the mixture, okay? So this is about this 2,000 kilojoule per meter cubed value. So mixtures of fuel should require that the same energy density or fuel mass density as this 50 gram per meter cubed. What this interestingly results in is it results in a mixture strength where the adiabatic flame temperature is about 1300 C. So 1300 C is a nice proxy, is a good sort of approximation for an ignition, and this is a terrible idea in general. Like, if you talk to combustion people, this is not a good idea, but it's a great sort of correlation and sort of empirical rule for an ignition temperature. So if you're able to reach an adiabatic flame temperature or flame temperature of about 1300 C, it suggests that you'll have this ignition process. So let me just also give a more quantitative way of identifying this mixture flammability limit. So if we had, and I'm going to go up a second, so if I said, okay, look, we have a fuel mixture where the fuel mixture has methane and propane, and so we have this 5% and 2%. So we have a methane and propane mixture. So we have a room where somebody was storing gases and somehow there was a release, and in this room we have methane and we have propane. Now the lean limit for methane we found out was 5%. So this is for CH4. The lean limit for propane from that page is 2.1%, okay? And in this particular compartment, we have, let's say we have 3% methane and 1% propane. And we want to understand if this system is, if it's flammable in this, and so we have obviously so we have 4% fuel, 96% air. There's a spark that's going off in this room. Will it blow up? Will we have combustion? Will we ignite a flame in there? So what we want to establish, well, there are a couple of different ways. We could just use the energy balance and see if we, from an energy balance perspective, if we would result in 1300 C adiabatic flame temperature for this mixture. But a simpler way of doing it is that comes from the energy balance, says that the mixture mole fraction, the mixture lower flammability limit, is equal to the sum of the individual component mole fraction divided by the individual component lower flammability limit. And so for this problem, we would have 1 over x sub L is equal to 0.03 divided by 0.05 plus 0.01 divided by 0.021. Okay. An Excel mix, so I don't have a calculator handy, but so I don't think we really need a calculator. So this is 0.6 plus approximately 0.5. So this is 1.1. So Excel did I do something wrong here? Xi over XLI. Okay, let's just play this out. So this isn't right because this is like 0.9, right? Okay, let me see something here. Okay, XL mix. Give me 1 second here. So right now I'm looking at I use Quantity's textbook for this fire class. So let's take a look at mixture values here. Okay, that's what I wrote there is right. And so maybe my math isn't very good. So Xi over XLI, sum 1 over X of L. So let's see. Xi over XLI. X. Okay, 1 over. I think this is right. 0.03 over 0.05. Oh, I'm sorry. Okay, now I see what I did wrong. Okay, so it's not the values in air, it's the values in the fuel. So it's our point, so I'll put that again, 0.03 divided by 0.04. And here it's 0.01 divided by 0.04. Okay, that makes a lot more sense. So it's 0.6 plus 0.5 divided by 0.04. And so XL is 0.04 divided by 1.1, which is like 0.036, okay? So the XIs that we're dealing with here, composition-wise, are the composition is the mole fraction in the fuel. And it makes sense because if you only had one component, then it would have to be 1 over XLI. So it's been a little while, folks, but that's clear. So yeah, so we know how to do mixtures of fuels in terms of the composition issues, and looked at what the issue is there. So another way that we can figure out flammability is using sometimes these flammability diagrams or flammability maps. And so these are useful because it's been tabulated. You have a graphical way of establishing flammability issues. So here's a flammability diagram for methane. And the idea is that this triangle, or this triangular graph or diagram, gives us a composition space. So this is N2, CH4, O2. And so any region here, so for example, the nitrogen, everything is red parallel to the axis where it's 0. So the nitrogen is 0, goes from 0 to 100 here. Oxygen goes from 0 to 100. Methane goes from 0 to 100. So the methane is 0 here, so the methane is always red in this direction. Nitrogen is 0 here, so the nitrogen is always red parallel to its 0 line. Methane is red parallel to its 0 line. Oxygen is red parallel to its 0 line. So oxygen is red in that direction. Okay? So we understand what directions these guys are red relative to. And we can establish, for example, so one interesting part about that, if we have no methane, so on the 0 methane line, and we're talking about air, we know that air is 21% O2, 79% N2. Spectacular. And now we can ask ourselves, well, what is the line that contains that exact ratio of N2 to O2, but now with increasing amounts of methane? The way we do that is we draw a line that goes through the 100% methane line vertex with this that connects this point, and we see that this is the air line. So there's an air line that goes right up there. I just want to change pen colors for that so that we make it clearer. So I'm going to make it blue because that makes more sense, right? Okay, so we have an airline. So we have our blue airline that just goes right there. It's a squiggly line because I just want to make sure it's clear. All right, now, because this is pre-computed from experiments, people said, hey, look, for methane in air, here is the envelope, for methane in all mixtures, here is the area where methane in all mixtures of O2 and N2 is flammable. And so you see how useful this is. Because first of all, it lets us identify so let's think about this, the lower and the upper flammability limits for methane. So let's make sure that's okay. So the lower flammability limit is this 5% value. The upper is where it crosses the air line, because upper and lower flammability limits are, when they're prescribed, they're discussed in terms, sort of normally in terms of air composition. But if you had another composition, you're doing fire safety in on space station. Maybe the space station oxygen to nitrogen ratio is not the same as it is on Earth, and so for whatever that composition is, you would have some other airline, air in quotes, and then you'd have different flammability limits associated with it. So this is, again, a useful way of determining that. So what I need you to do is I need you to know how to use this 3-component flammability diagram. As I said, the textbook that I often refer to is this Quantitative textbook. And so this is Fundamentals of Fire Phenomena. And so this is what I normally teach this class from. And the coverage for flammability diagrams is, I believe, Chapter 4. So Chapter 4 in Quantitative has the flammability diagrams and all the different issues associated with that. See if I have that methane example. So yeah, he'll talk about things like the flammability diagram and some of these other issues that I've been discussing. So here I'm showing an intermediate location, 50% methane, 25% N2, 25% O2. Remember, O2 reads in this direction because this is the zero value of O2. This is the zero axis. It reads parallel to that. Here's 0 for N2. It has to read parallel to that. This is 0 for methane. It has to read parallel to that. So it pushes us to a location like that. So we can answer questions like, how much nitrogen would have to be added to a mixture of 50% by volume methane, 40% O2, 10% N2 to make it non-flammable? And so we identify the initial location. The initial location is A. So A, again, 50%, 10% N2, and 40% O2. So we start off there. We have to go to 100% nitrogen. So we push this thing towards 100% nitrogen because we're basically fixing our methane to O2 concentration. Find out that we get to about a point B that allows that to happen, and that point B graphically corresponds to about 40% CH4, 30% N2, 30% O2. So think about how quickly we were able to do that. And again, it's just a graphical way of being able to do that evaluation. You know, we can do it more sort of computationally. We can do it in a more computational form, sort of more computationally quantitative form. So we can talk about our initial mole fraction of methane and O2. We understand that our final, well, this isn't even really, you know, the computational form, because in this case all I'm doing is I'm saying what the final form is, knowing the answer. Sort of a more sort of detailed view of this, let me just get this going. A more detailed view would say something like this. It would say, okay, well, X mole fraction of that plus the mole fraction of this guy plus the mole fraction of the N2 must be equal to 1. Initially, XCH4 over XO2 is equal to, what did we say? Was it 0.5 over 0.4? I think so. 0.5 over 0.4. So I can substitute in here, and then I have XN2 plus XO2 times 1 plus 0.5. So XCH4 is 0.5 over 0.4. Is equal to 1. You see? So I substituted, I know this relationship between these two guys, so I forced this to be in terms of one equation with these two unknowns. So basically all I have to do is pick out an XN2 value, and I know what the XO2 value is because XN2 plus XO2 is equal to 1. So this says that, I'm going to write it like this, XO2 is equal to 1 minus XN2 over 1 plus 0.5 divided by 0.4. So this, in some sense, this is my sanity check. So I could have gone over here and said, okay, pick an xn2 value, whatever it is, you know, so xn2, say 0.5. So minus 1.5 divided by this guy. And so roughly, this is what? 0.5 divided by 2, 0.25. So it would say that at 0.5, my XO2 better be about 1/4. So boom, like that. So I know that along this line, I've held my composition fixed. I can draw that line, and I see where it intersects the flammable region. And again, I'm able to identify what's going on. Really quickly, I'm going to go over flame quenching. So what we talked about is flammability limits. We understand the flammability limits set the overall extent of which a mixture is flammable. I cheated you. I didn't tell you anything about rich flammability limits. And so rich flammability limits are a problem. The reason it's a problem is because we don't really know what the composition is going to be in the rich regime. And so for rich flammability limits, a correlation Zebetakis is XU is equal to 6.5 square root of XL. So XL is easier to figure analytically. So if we, for some reason, don't have a table, if we have a table, we're going to get both of these guys. We're going to get XU and XL. But this one is easier to get analytically, either by using our 1300C or our mixture rule. This guy then can come from that guy using this simple rule. Okay, flame quenching, what does this mean? Basically, flame quenching refers to, for the most part, thermal processes that cause the reaction to stop. And it really referring to typically premixed flame quenching. I mean, there are ideas of non-premixed flame quenching, but that's not a typical sort of way of thinking about non-premixed flames. When we talk about non-premixed flames, there are issues that cause the flame to extinguish. Typically, these have to do with residence time issues, and we'll talk about when there is not enough time for the fuel and air to be together to react. But for premixed flames, imagine that you have a cold wall, and you have, again, reactants, fuel and oxidant near that wall. This flame wants to propagate all the way into that wall. If this wall were adiabatic, if this wall were hot, the flame would easily propagate all the way to the wall, consume everything there. If this wall is cold, the nature of the reaction is that you have to have high enough temperature to overcome this activation energy barrier to allow for the flame and the reactions to continue. So if you have this energy barrier to get reactions to take place, but you're inhibited because you have this huge thermal reservoir, this heat sink, this wall that's cold, it means that near that wall you can never get the flame to propagate. And so for single-sided flame quenching, so when we have just a wall, typically people talk about stagnation and sidewall quenching. From a fire safety perspective, these are less important and relevant than what's called double-sided. So if you have a cold wall channel and you have a flame that is trying to propagate, so maybe you had a plenum up here where a flame was ignited and it propagated all the way over here, and you're asking the question, is it going to be able to continue to propagate into this channel so that maybe it propagates into another open plenum down there? Similar ideas hold that if these walls are cold, you lose so much heat to the walls that the flame cannot propagate through the channel. And so this process is what's important in a device called a flame arrestor. So a flame arrestor is it's a safety device that inhibits the connection of a flame between, for example, two volumes. So you put it in safety systems so that this reaction process doesn't take place. And sort of the simple idea is that there's something called a Peclet number. So a Peclet number is really just a characteristic velocity, a characteristic length scale, divided by a characteristic diffusivity. And in this case, it's a thermal diffusivity. And for this problem, UC is the laminar flame speed, LC is the diameter of the channel. So it says this. It says that if this Peclet number is less than a critical value, in this case the critical value is about 40, that the flame will not propagate into the channel. If it's greater than that, you've got problems. So my favorite example, methane, right? 0.5 meters per second. So let's ask under what condition is this thing 40? 20 times 10 to the minus 6 meters squared per second times my L characteristic, my diameter. Let's say under what conditions is this thing 40? So 0.5 dc is 800 over there. So we have 8 times 10 to the minus 4, and we multiply by 2, and we see that dc looks like 16 times 10 to the minus 4 meters, which is 1.6 millimeter. So if I have millimeters, it says approximately, if I have millimeter diameter porous element plugs, so I can engineer then a system where I have these small plugs, so almost like a monolith or a catalyst or something like that, and I can use these guys in a large channel. So I've got a big channel where the diameter is much larger than my quench distance, but I fill it with a porous section where my pores are millimeter scale. If I have a flame propagating through there, I arrest it. I stop that flame at that interface. It can no longer quench in, it can no longer propagate through and perhaps cause an explosion downstream because of this, this flame arrestor. The scaling is actually pretty simple. And the scaling idea for this is that, well, the Peclet numbers, the reason why this might occur is do I have energy in my flame relative to how much I get in terms of losses? And so you say, okay, well, look, the amount of energy that the flame carries is basically TB minus T wall or T unburnt. That's my enthalpy, enthalpy flow in the flame. My heat loss characteristics are basically K over D, so that looks like a heat transfer coefficient, times, again, TB minus TU, okay? So this is my heat losses. This cancels out, and you see that the characteristic value is SUD over K over rho C. So it has to look like a Peclet number, and the value happens to be about 40. Flame stabilization. So all this says is that because the flow, because of no slip and cold walls, we get lower flame velocities near the wall, and these lower flame velocities and lower required flame speeds are the thing that anchors the flame. Ignition energy, the thing I want you to know about this is that the strongest flame, like these alkanes, requires almost no energy. So electrostatic discharges will easily set this thing off. So things like electrostatic discharge, static energy, basically like just a shock, will cause ignition. As we go towards our flammability limits, of course, it takes more and more energy to ignite, and so that's another way of inhibiting this system. There are temperature effects on flammability, so as we go to higher temperature, the lower flammability limit decreases, and there's some weird things that happen with the upper flammability limit. Again, if you think about it more or less as delta T is equal to the mass fraction times the heat of combustion divided by C sub P, and we want to reach some final temperature, say, of 1300 degrees C, then this is on the lower limit. Then as we increase T0, we need less fuel to get to 1300 C. Okay. One last thing. Turbulent premixed flames. So we never talked about turbulence. I mean, turbulent premixed flames are not as important for fire issues as they are for engine applications, whether it's, again, gas turbine or internal combustion engines. I guess one area that it's important, and particularly in a nuclear area, is that, say you had a hydrogen leak, and this hydrogen leak is pre-mixed with air, and you get this propagation process initiated. So there's a spark, you get a laminar flame initially. Eventually this laminar flame gets distorted because of the flow. So we haven't really talked about turbulence, but turbulence is a nonlinear sort of flow mixing processes that are going to happen in these fluids. And so the chaos in the flow, the eddies and the turning in the flow, are going to wrinkle the flame itself. So initially the flame itself wrinkles, and as it wrinkles, it consumes more and more reactants per unit of the duct area because it's more corrugated. And eventually, as it accelerates, it's pushing the stuff ahead of it faster, and it gets more and more turbulent itself. So there's a method and a process by which this system becomes turbulent just in terms of the instabilities and the initiation. To first order, the turbulent burning speed, and so this is not a fundamental issue because it's flow dependent, but it looks like the laminar, which is this fundamental relationship, it looks like the laminar flame speed times really this area ratio of the actual area of laminar flame surface contained in an average. So it's sort of a weird thing. It's a little bit backwards here. So I should call this AL and AT to be consistent with this. It would look like this AL, where these are individual laminar elements, and this AT is some average description, averaged area. And so when I have AL over AT large, because it's this, and so the first thing that may have come to mind to you is that maybe it's a fractal description, and that's exactly right. So one model for this is a fractal flame propagation model, and again, the coast of Norway is that if I look at this ratio being large, maybe 3 or 4, then I get an enhancement in my flame propagation speed. Okay, that's all I want to say for now, and so we will continue with, I want to say, more general ignition processes, spontaneous ignition, more general ignition, and ignition of liquid vapors. All right.